The SWITCH project represented the maximum operational functionality for solid oxide cell technology. In this project, we develop a prototype and a technological concept where a solid oxide cell it is used in a reversible mode between fuel cell and electrolysis. This system is able to produce hydrogen when it is available electrical source from, let me say, renewable energy, solar or eolics, in electrolysis mode, but it is able to produce hydrogen even in fuel cell mode, thanks to biomethane or methane input. In this way, it is possible to produce hydrogen with the methane. A part of this hydrogen is used in the fuel cell to produce electricity power, enabling different type of business case where electricity can be sold in order to exploit some revenue in the cost of the hydrogen. The SWITCH project and the prototype cannot exist thanks to a strong collaboration between the partners of the consortium. This system is quite complex and has required a lot of effort and collaboration between any partner in order to define any small and teeny detail about the prototype and to verify the proper behavior in the operation.
In this SWITCH project, we have performed lifecycle cost analysis and lifecycle assessment. When we talk about producing hydrogen, there are many different ways to do it. One of the common methodology is using steam method reforming, where we apply fossil fuel. But this has a problem. This process basically can release a lot of CO2 into the atmosphere, and this is not considered as environmentally friendly. So what we really need to do is move away from fossil fuel and start looking at renewable energy sources instead. And that is where electrolyzer powered by renewable electricity come in. It is considered as a key part of the solution. And actually, we're quite happy that this approach has been successfully applied in our SWITCH project. There are different types of electrolyzer, such as alkaline electrolyzer, ion exchange membrane electrolyzer, polymer electrolyzer, and also solid oxide electrolyzer. Now, while we know that the SOE still have a lot of space to improve, compared with alkaline or PEM technology, what we actually found in the SWITCH project is that it's quite interesting. Basically, under the most case scenario, we found that a solid oxide electrolyzer is more efficient. It tends to have a lower environmental emission during the hydrogen production. Moreover, this solution doesn't rely on any critical or rare raw material usage in the stack production, and that is considered as a long-term solution, especially for our SWITCH project. Finally, a solid oxide electrolyzer can work in its reversible mode as solid oxide fuel cell, and this unique feature from SWITCH project actually gives us a solid solution in answering which technology can be actually used to storing energy, and that is pretty cool.
In the SWITCH project, we try to demonstrate the reversible operation of a high-temperature fuel cell and electrolyzer system. At EPFL, we are assisting this research by a long-term laboratory test of a reduced size model of a short stack run in the switching mode. We have a particularly designed cell of the same size as used in stacks from Solidera, the stack partner. This segmented cell is mounted on top of a short stack, 5 to 6 cells, itself mounted on top of a base plate, where we have the possibility to come and contact the segmented cell with its own current pickup for each segment. This allows us to follow, during operation, the local current density, the local voltage, and the temperature from inlet to outlet. We have run a test for over 6 months with daily switching between fuel cell and electrolysis operating modes to simulate the actual reversible operation of the device. We have been able to show that there is no degradation of performance due to the switching, that in fact there is a slight increase of the performance. And secondly, for the electrolysis mode, we have tested different electrolysis voltages, 1.2, 1.3, 1.4 volts, that stand for endothermal, thermoneutral, and exothermal operation. We have been able to show that the thermoneutral Operation, as expected, is indeed the most favorable one because we have the most homogeneous temperature distribution from inlet to outlet. So it is the experimental proof of something that is expected theoretically for high temperature steam electrolysis.
Welcome to Solidera. We are a world key player in the field of solid oxide fuel cell and solid oxide electrolyzer. My name is Antonello Nesci. I'm the General Manager of Solidera Switzerland, one of the Innovation and Development Center of the Solidera Group. We are very proud being part of the SWITCH project.
To design the SWITCH systems process, we creatively utilized experience from previous European projects. We developed a process flow diagram for the balance of plant, simulated it in 2 hydrogen production modes and 3 power production modes, including hydrogen production, and evaluated startup and shutdown phases. The simulation results guided the sizing of balance of plant components, and real component behavior was simulated to ensure alignment with SWITCH project's expectations. Concurrently, a significant effort was put in assessing the risks associated with the system. Our goal was to identify safety risks and reduce them to an acceptable level. Ultimately, we compiled a comprehensive documentation package, including manuals and datasheets.
For the SWITCH project, I have supervised the production team for the hot module prototypes assembly, including stacks and hot balance of plant. Within this project, we have developed a fully reversible stack that can be operated both as a fuel cell and electrolyzer. This new version of stacks, integrated in a large stack module, allowed Solidera to improve the performance of our electrolyzers and our know-how in the field of hydrogen production. The prototypes of this project have been designed to be easily suitable for industrial applications.
I'm part of the automation team in charge of the development of both safety and control logic for the hot modules used in the SWITCH project. SWITCH allowed us to enhance our knowledge in controlling more efficient, reversible hot modules that can be easily integrated into complete hydrogen production plants. Thanks to SWITCH, we have been able to refine our operating mode boundaries to create simpler control architecture and interfaces to better fit customer needs. Both our control and safety logic is now well defined and has been validated both in simulation and real test conditions, ready for industrial application.
I'm a project coordinator at Solidera in charge of SWITCH project. As a partner of SWITCH, Solidera has extended its fuel cell know-how in order to develop high-temperature steam electrolysis operation, which gains a huge interest in industrial customers willing to reduce their CO2 emissions in their processes. The development of SWITCH prototype allows Solidera teams to enhance the experiences in designing, building, and controlling efficient reversible hot modules, easily scalable to realize a complex system to meet customers' expectations.
We work on solid oxide cell technology, the core technology of SWITCH. In SWITCH, we contributed in stationary and transient simulations and led the work package for experimental investigations. This includes analyses of SolidEra's technology, from cell to module level. EPFL performed segmented cell tests, FBK on stack level, and finally we at DLR on a large stack module. This module was tested for more than 2,400 hours in very close collaboration with SolidEra on our test rig Galactica. The entire operating range of SWITCH was demonstrated in electrolysis and in fuel cell operation. For example, 53 kilograms per hour of hydrogen were generated in electrolysis with a power consumption of 75 kilowatts. In fuel cell mode, 25 kilograms of hydrogen and 22 kilowatts of electricity were generated. Furthermore, we were able to fully characterize the large stack module on different temperature levels, conversion rates, and endo-thermoneutral and exothermic operation. Characteristic UI curves were measured and the area-specific resistance analyzed. Beside these stationary results, switching between the modes was demonstrated in conservative 30 minutes. A model of the large stack module was developed and validated using our transient simulation framework Tempest. This proved that SWITCH produces hydrogen, mostly green, always secured. Thank you and stay tuned.
Within SWITCH project, idea lists the overall system assembly, integration, and testing, in addition to the development and design of the so-called cold section, like the gas handling and the pressure swing absorption unit for the hydrogen purification and recovery. The SWITCH prototype system comprises two large stack modules that represent the core of the system. The prototype has been designed for a production capacity up to 100 kilograms per day of hydrogen once operated in electrolysis mode. Within the SWITCH system, we can identify two major sections. One's called odd section, and the balance of plant component of this section mainly consists in all the equipment needed for fuel processing, like a pre-reformer, a burner unit, and the steam generation. And beside the odd section, we have a cold section that is designed to provide all the main feed stream, like the natural gas, water, air, and utility, at the required conditions in terms of temperature and pressure level, as well as composition. When green electricity is available, for instance from a renewable resource, the electrical power is used by the prototype to generate hydrogen via electrolysis reaction. That is an electrochemical reaction occurring in the large stack module that converts the steam into hydrogen. The stream from the large stack module are then further compressed and processed in a pressure swing absorption unit, where the hydrogen is purified and recovered at a neither purity level for the end user, like for instance hydrogen refilling station. When green electricity is not available, the prototype can work as a hydrogen and electrical power generator by converting via a combination of a steam-engine reaction and electrochemical reaction methane-rich fuel streams into a mixture of mainly hydrogen and CO2. And one of the features of the SWITCH prototypes, beside the reversible operation mode of the large stack modules, is a multifunctional PSA unit that is able to process and purify wet hydrogen, as well as reformate streams that contains, beside the hydrogen, other gases like CO2, nitrogen, and unconverted methane. So overall, the SWITCH prototype can ensure continuously hydrogen production by using multi-sources as green electricity or methane-rich fuel streams.
ECO plans and designs the communities and cities of the future. The results of our work are green buildings, efficient infrastructure, and access to clean energy and water. In SWITCH project, we supported FBK in the realization of Work Package 7, dissemination, communication, and exploitation. We managed the exploitation activities of SWITCH. We conducted research of European markets to find potential customers, analyzed market conditions for technology upscale, and prepared business cases for technology applications of the SWITCH system.
And the result of the project can be marketed as one of three options: sold hydrogen, sold SWITCH system, and sold as a license for the system. Hydrogen has a high potential for use in transport to fuel buses or industrial vehicles. In hydrogen terminals, it can be used for industry purposes. The examples of industrial segments that need a continuous hydrogen supply for proper operations between 40 kilograms and a few tons per day are filling stations, food, oil, and glass industry interested in emission reduction. We think that companies could be interested in the SWITCH solution. The result of the SWITCH project is to support sustainable development policy to reduce carbon dioxide emissions, carbon footprint, and price of producing and making hydrogen available. We believe that hydrogen and electricity users, European countries with a low carbon electricity mix, or public transport companies will be interested in the result of the SWITCH project.
We established the
a long-lasting collaboration with in European research centers like the EPFL from Lausanne, the DLR, the German Aerospace Center, as well as with important industrial stakeholders. We have a strategic collaboration with Solidera. We collaborate with Highgear as a system integrator, and with Shell and SWECO as end users and engineering company for the final technology solution. As the Center Sustainable Energy, we are bringing forward an acceleration of the deployment of technologies to the market. We are preparing novel forms of collaboration with industrial stakeholders, even creating a new center providing the center of real scale, industrial scale validation technologies and a unique location where we could collaborate together. SWITCH, continuing the activity started with the CH2P, is one key solution and one key technology we are trying to push forward in the market in this accelerated way of technology deployment.